A hypothesis test asks whether one parameter equals some value, but how do you compare two whole models? The Bayesian answer is a single number, the Bayes factor. Start with odds. Before seeing data, you have prior odds on the two models. The Bayes factor is the ratio of how well each model predicted the data you actually observed. Multiply, and you get the posterior odds. The Bayes factor is exactly the weight of the evidence. That predictive term is a marginal likelihood, the likelihood averaged over the model's own prior. Averaged, not maximized. A flexible model spreads its prediction across many possible datasets, so it is thin everywhere. The simpler model bets narrowly. If the data land where it bet, it wins, an automatic Occam's razor, with no penalty term added by hand. Reading it is easy. A Bayes factor of 10 means the data are 10 times more likely under one model than the other. By convention, 3 is substantial evidence, 10 is strong, 100 is decisive. And unlike a p-value, it cuts both ways. A Bayes factor of 1/10 is real evidence for the simpler model, not just a failure to reject it. The catch is the prior. The marginal likelihood integrates over it, so a Bayes factor never forgets which prior you chose. Make that prior vague enough and the evidence drifts toward the simpler model no matter what the data say. That is Lindley's paradox. So keep priors proper and report how much the answer moves when you change them. Bayes factor, a ratio of marginal likelihoods, turning prior odds into posterior odds. It weighs evidence in both directions, and it pays for complexity automatically. Next, the result this whole course has been leaning on, the law of large numbers.